Bharat sir? Okay. So, friends, good evening. I'm extremely sorry. I'm almost 20 minutes behind the schedule. Unforeseen, commitments. So, therefore, kindly bear with me. So, yesterday we have discussed many aspects about convection heat transfer. Very unfortunately, many of you have given a feedback that you could not view this, and many of you are requesting for the repetition of the entire convection. Maybe it takes longer time because we need to keep up with the schedules. Some of you, if you have problems, I think the lecture video is available in YouTube. Maybe offline also, you can maybe anytime you can view that. If you have any issue viewing that, probably you can contact JNTU officials. The coordinators' phone numbers and email IDs are kept in the notification itself. So you can contact them, they can provide you. So you are not asking me to repeat the entire convection heat transfer, but of course I'll start talking about a few salient issues and then continue with our lecture. One couple of them asked me to explain the difference between Biot number and Nusselt's number. I think I took sufficiently long time and explained the difference between Biot number and Nusselt's number for a simple reason that it is always confusing to you. See, I told you one final explanation as quickly as I can. We did discuss about the transient heat conduction, particularly the lumped heat capacity, lumped systems. In the lumped system, whole body will be at one temperature and the resistance inside the solid. When you are talking about heat transfer, resistance experienced for the heat transfer inside the solid and the convection heat transfer taking place outside the solid, these are compared. See, conduction inside a solid and convection outside the solid, these are compared. And that's how Biot number came into picture. Biot number by definition is internal resistance to external resistance. Internal to external. External. Right. What is internal? Internal is within the solid. What is external? Outside the solid, that is convection heat transfer. So within the solid, we know that conduction resistance is L by Ka and external resistance is 1 by Ha, and therefore we got this equation HL by K. Right? And where here, very quickly, I ask you this question, where L is the characteristic dimension, we said. How it is calculated? LC is equal to volume divided by surface area. This is also I have explained while explaining the answer. So L is a distance. It depends on the geometry of the solid. Geometry of the solid. H is the heat transfer coefficient associated the fluid and solid heat transfer coefficient. So whatever the fluid solid combination, that will be given in the problem. What is K? What is important here is K. What is K? K is that of the solid. Please remember, whenever you are talking about Biot number, you use thermal conductivity of the solid in the denominator. Whereas what is Nusselt's number? I said, though the convection heat transfer is, when we talk about free convection or force of convection, though the heat transfer is predominantly because of the convection or bulk motion of the molecules, conduction heat transfer is also not ruled out. So that means when you have a plate, some heat is moving out of it, some heat Q is moving out of it, plate is at a temperature TW, food is at a temperature T infinity, obviously TW should be greater than T infinity. Then the heat transfer that's going is because of convection as well as convection. So what do I say? The heat transfer, heat transfer from solid to fluid is a combination of an addition of the pure convection. What do I mean by pure convection? Bulk motion of the molecules. Molecule going to the hot spot, taking the heat and going back. So that is the bulk motion of the molecule. Also due to molecular interactions within the fluid itself. I'm talking about this zone. I'm not talking about a solid at all. I'm not talking about this. I'm talking about the fluid. When fluid is participating in the heat transfer process, part of the heat is removed from the plate by convection heat transfer because of the molecular movement, and part of the heat is taken away from the plate due to molecular interactions or momentum exchange taking place with the molecules. Now, everything belongs to that of a fluid, and therefore the heat transfer is because of convection and conduction. Now, someone can ask you a question. Okay, Q amount of heat is convected from the from a particular solid surface. The fluid is X or Y, whatever the fluid that is, air, kerosene, or whatever. Now, how much do you think is transferred by pure convection? How much do you think is transferred by conduction? So when when they ask you this question, then you should be in a position to answer or explain how much is by convection, how much is convection. I told you a few specific cases where fluids like gases, where the intermolecular attraction is very, very weak, molecules can very randomly freely move from one place to the other within its domain, fluid domain. So therefore, the resistance for the bulk motion of the molecules is absolutely minimal. And we also have studied at conduction heat transfer that the thermal conductivity of the gases is very, very low. That means when conductivity is low, the resistance is very high. So for a gas, the conduction resistance is very high, whereas convection resistance is very less. And take, for example, a liquid metal, like flowing lead or something, liquid metal. The viscosity is very, very high. The molecular density is very, very high. Intermolecular attraction is also very high. The molecules cannot very freely move. In such a case, I say convection resistance is very, very high, whereas the conductivity of the liquid metal is very high, and therefore conduction resistance is less. So, from case to case, also we did discuss about viscous fluids. Viscous fluids, by virtue of the viscosity, the resistance offered to the force, the molecular movement will not be very free. And in that case, it is not very conducive for convection heat transfer to take place. So when it is not conducive for convection heat transfer, convection resistance obviously should be high. So, summarizing everything, Nusselt's number compares the conduction resistance and convection resistance within the fluid itself. That's why you just look at this domain I am drawing here. Within the fluid, how much of conduction resistance, how much of convection resistance. Whereas here, one resistance is within the solid, one resistance is outside the solid. So when we are writing an expression for Nusselt's number, it is also HL by K, where K is that of fluid. I don't need to give you any more explanation. Thermal conductivity is that of the fluid in case of Nusselt's number. Thermal conductivity is that of the solid in case of Banach number. Okay, so absolutely you cannot compare between them. One is Banach number is talking about, we use it in transient heat conduction. It compares solid resistance versus convection resistance outside. Whereas in the Nusselt's number, we are comparing the resistances offered by the same fluid. Fluid air aithe, convection resistance of air and conduction resistance of air. And that's how you take thermal conductivity. of the fluid. Hope I've explained it sufficiently. Must be, for those who have understood it, must be a great repetition. Bear with me. Okay. So, someone said the PPTs are different. I don't think the PPTs are different. Anyhow, if you feel so, I'll upload all the PPTs, right? Okay. So we were talking about the dimensionless numbers. Very quickly, I have talked about the three-dimensionless numbers. I initially was talking to you about closure convection for a flat plate, and I just explained what is hydrodynamic boundary layer, what is thermal boundary layer, and the fluid flow pattern over a flat plate. Initially, it is laminar, then transient, then turbulent. I have given you an analogy also, maybe linking to your own student life from elementary school to the college, how you drift everywhere when you come to the college, how turbulent you become when you come to college, and how organized or laminar you were when you were in your elementary school, at least the early years of elementary school. I just try to draw an analogy. Fine. Hope many of you remember that. Okay. And what is the parameter that influences? It is the Reynolds number. Now, Reynolds number straight away talks about the flow patterns. Reynolds, based on the Reynolds number, you give it. And when Reynolds number is normally less than a critical value, normally the flow is treated to be laminar, and when Reynolds number is greater than a critical value, we call it as turbulent. What is Reynolds number? Inertia force divided by viscous force. This also we have made it very clear in the last class. What is inertia? What is viscous force? How these forces are coming into picture with an explanation I gave. So, knowing Reynolds number, you can visualize what kind of a flow it is, whether it is turbulent, whether it is disturbing, whether disturbances are many, or whether it is laminar, organized, and based on that you can follow the entire calculation. Also, I spoke to you about the other dimensionless number called Prandtl number. What is Prandtl number? Prandtl number is defined as molecular momentum diffusivity to thermal diffusivity. And that's what I said as an equation form, mathematical expression. I said it is nu by alpha. The thermal diffusivity is alpha, momentum diffusivity is because of the viscous effects, and therefore nu is taken in the numerator. Or if you convert that into slightly other form, substitute the values of alpha is equal to k by rho Cp, then the whole equation of Prandtl number becomes mu Cp by k. Mu Cp by k. And most of the gases, the Prandtl number will be close to 1. That's what we have discussed. And also, very importantly, I did talk about the comparison between the hydrodynamic boundary layer and the thermal boundary. When Prandtl number is less than 1, Prandtl number is equal to 1, Prandtl number is greater than 1. When Prandtl number is less than 1, I told you that the thermodynamic boundary layer, when thermal boundary layer will have greater thickness than hydrodynamic boundary layer. When Prandtl number is equal to 1, both boundary layers superimpose over each other. Delta T is equal to delta H for all x values when you travel along the x direction. So I said this, right? Okay. Now, when Prandtl number is less than 1, what does it mean? Numerator is bigger and denominator is smaller. What is numerator? Molecular momentum diffusion. Okay. Thermal diffusion is in the denominator. Alpha is in the denominator. When it is less than 1, thermal diffusion is greater than the momentum diffusion. So what does it mean? So when it is Prandtl number less than 1, this will become delta T and this will become delta H. Meaning hydrodynamic boundary layer is thickness is less than the thermal boundary layer at all x values. What is hydrodynamic boundary layer? What is thermal boundary layer? I have explained it to you. Where you feel the velocity variations, it is hydrodynamic boundary layer region. where you find when temperature variations, you find you call it as thermal boundary layer. So when a fluid is flowing over a flat plate, don't think that you find this layer everywhere, but it will be in the close vicinity of the plate only. Somewhere here, it is all free stream velocity. It is not within the boundary layer limits. So beyond the boundary layer also, there is some flow happening, which appears to be not influenced by the thermal effects as well as the boundary layer. So for when Prandtl number is equal to 1, that's what I said, delta T should be equal to delta H, because numerator and denominator are equal. The diffusion of momentum as well as diffusion of energy both go to only the same distance, and therefore it is so. So for all Prandtl numbers greater than 1, quite obviously your numerator should be high. So your delta H is high, delta T is small. This is what I said. So Prandtl number has a purpose. Whenever we said that, Prandtl number indicates a comparison rather between hydrodynamic and thermal boundary layers. You can visualize what kind of a flow it is. And also I said the Nusselt's number. Nusselt's number already I have explained. So Nusselt's number always talks about, is the heat transfer more because of convection or less because of convection. When Nusselt's number is very, very high, your convection heat transfer will be very high. Whereas when Nusselt's number is low, convection activity, then heat transfer coefficient H, C is specific heat, V the velocity in force of convection. In force of convection. So these are the 7 parameters that we normally talk about. Rho, L, mu, K, H, C, P, V. These are 7 parameters. They all of them, one or other, use all the 4 fundamental units, because L has length unit, CP has density as mass unit kg, and thermal conductivity, heat transfer coefficient have temperature parameter. So HCPV, of course, what happens with when each one of them vary. But as a group, straight away look at it. When Reynolds number, close your eyes and say, what is the Reynolds number? Reynolds number is low, the flow ought to be laminar. When Reynolds number is high, flow should be turbulent. And how is the flow going? Molecules are randomly moving everywhere. No, when Reynolds number is low, molecules are moving orderly. See, by just knowing one number value, you can really understand what nature of fluid flow is taking place there. Right? Prandtl number. So just now I have drawn the figures. The hydrodynamic boundary layer is more, or thermal boundary layer is more, or whether heat influences are felt to a greater y distance, or viscous influences are felt to a greater distance. You can know simply by knowing the value of Prandtl number. And similarly, when Nusselt's number is there, you can understand whether molecules are freely moving. Is it majority of the heat transfer, is it because of convection or because of convection? So that's how I said. And also I was talking to you about the skin friction. The skin friction, I said, from the Newtonian fluid theory, tau is equal to mu dou u by dou y, mu dou u by dou y, and any fluid that obeys that, we called it a Newtonian fluid. Any fluid that is not obeying it, we called it non-Newtonian fluid. So the tau is the shear stress, multiply tau with the area, you get the drag force. You got the drag force. Now, why is it important? Because when a fluid is flowing, when the fluid is flowing, the fluid viscosity, the wall friction causes a certain force to be applied, and this results in pressure drop. So therefore, you need to know what is the force acting because of the fluid flow over that. And this is more important when you are talking about, objects which are, moving in a fluid situation, objects which are moving at great speeds in a fluid situation. Maybe it can be your automobile moving on the road against the atmospheric air, or your aeroplane moving at tremendous speeds, or your jet moving, anything, anywhere, the force is very, very important. Maybe to make you understand, I'll just tell you about a simple example, what you all like it. You know, have you ever heard about ever heard about cricket ball swinging? Swing in the cricket ball. There is a difference between spin and swing. A spin bowler is different from a swing bowler. So normally medium paces and fast bowlers swing the ball. What do you mean by that? If it is spinning, the ball comes rotating. When once it is pitched, it takes a different direction. That's spinning. What is swing? When the bowler releases the ball takes a curved path, right? The ball, even before hitting the ground, the ball takes a curved path, right? So when the batsman is somewhere here, when the bowler is releasing the ball from here, maybe in the air itself it moves in this direction. We call this as in swing. We call this as upswing. Now, how is that a bowler is generating this curved path for the ball within the air itself? No, normally when you release the ball, it should be going straight. And many of you know how swing is produced because all of you are great cricket players. Now, when a cricket ball is there, you all know they will be rubbing against their pants, right? So they always keep one surface very, very smooth, whereas the other surface is rough because of it's pitching repeatedly on the pitch or bat striking it or rolling on the ground. The other half becomes rough. The leather here will be slightly damaged on its surface and therefore it becomes rough. So when you are releasing the ball is piercing through the air, and what is happening? The air is moving against the smooth surface and also air is moving against the rough surface. So the rough surface offers greater drag force because of excessive friction. How is that excessive friction is appearing? Because it's a rough surface. Whereas the other surface, air can very easily slide on it because it is very smooth. Or otherwise, he is very deliberate, he spits on it and he rubs on it. Please remember, they don't rub the entire ball on completely. They only rub the ball only on a half side. So one half is made smooth, one half is rough. That's what ball tampering is. Now, certain times, they use cool drink caps to make it very rough. Now, what is the intention? When you make one surface rough, the air moving on it offers maximum resistance. So when ball is released, the drag force on in the ball that I have drawn here, the drag force on the left side is very, very high, whereas on the right side it is not as high because it is smooth surface. So therefore, the air is offering resistance on left side, whereas it's not offering the same resistance on right side. So ball is moving towards in the outswinger push. What is in swing? Reverse the ball. Reverse the ball. So you make this smooth and you make this rough. This surface rough. While holding the ball, the bowler holds it in that way, and therefore maximum resistance is offered. Ball moves in the in-swing direction. So drag force and lift forces are very, very important, and there are a number of calculations that we make every day in order to make these automobiles moving, aeroplane moving, and last even cricket players also, even golf players, everyone, they use, even football players use this. So, and of course, that's a technique, right? So we did talk about the equations that give you these parameters. In a force convection situation in a flat plate, that's what we were discussing in the last class. The force convection over a flat plate, we talked about hydrodynamic boundary layer thickness. You can use this first equation to calculate hydrodynamic boundary layer thickness. If it is a laminar flow, turbulent, it will be a different equation. So all these equations that I have listed here are laminar. So skin friction you can calculate. Why do you calculate skin friction? To calculate shear stress. And why do you calculate shear stress? To calculate drag force or frictional force, FF. So how do you calculate shear stress? CF into kinematic viscosity, half rho v square. So that is given here. CFX can be calculated. When once you calculate CFX, you can calculate, I talked to you about Reynolds analogy and Chilton-Colburn analogy, and that gives you specific value of CFX. When once you know the CFX, you can calculate shear stress, and therefore you can calculate, the drag force or frictional force. And I said Nusselt's number can be calculated as function of Reynolds and Prandtl. So Reynolds is given by rho v L by mu, Prandtl is mu Cp by K, Nusselt's is HL by K. And also very clearly, categorically, I have stated the difference between local heat transfer coefficient and average heat transfer coefficient. Right. And for all laminar flows, I told the local average heat transfer coefficient is twice that of the local heat transfer coefficient. When you multiply the local heat transfer coefficient value with 2, you get the average value. That's it. What is the difference between average and local heat transfer? I told you. Now, flow over blunt bodies, I told you, flow separation and pressure drag also I said. See, when a fluid is flowing, what is pressure at the frontal area, what is the pressure at the back area, and in some of the cases when flow separation is taking place, you will have negative pressures, and therefore the pressure difference also drags the vehicle, and that is called a pressure drag. Okay, so I was explaining this to you towards the end of it. The coefficient of drag, which is a combination of skin friction, that is the drag force, the frictional coefficient, and also the pressure coefficient, drag coefficient for pressure. So sum of it is the total thing. For all laminar flows, I said, the CD pressure will be almost negligible because fluid is very gently flowing. It's not moving at a great velocity. It is very, at a minimum speed. We all know that it's organized flow. And therefore, the pressure differential is not much across the body. And therefore, you can ignore CD pressure, which is the coefficient of drag for pressure difference. Okay. The frictional drag will always be there. Huh? And we did talk about wake region. I said how dangerous it is for a second flight to go behind the first flight. The wake region will be deadly. And also I said for all practical flat plate flows, you estimate the properties. What are the properties you estimate? To solve the convection heat transfer, you estimate the properties like rho, mu, Cp, K, etc. And you all estimate these properties of the fluid. What is the fluid participating in convection? If it is air, you take the property of air. If it is kerosene, you take the property of kerosene. If it is water, you take the property of water. But at what temperature? So I said, if plate temperature is at TW, fluid free stream temperature is T infinity, you always get the average temperature, TF. The film temperature, that's what I call. The film temperature is the average of wall and fluid temperature. At this temperature of TF, you calculate the properties. These properties are available in data book, and you estimate these properties, not calculation. You take these property values of that fluid corresponding to this TF temperature. So TF is the average temperature between wall and. So this is what we discussed in the last class. Okay. Now, so one another thing I just wanted to tell, Reynolds number is rho v L by mu, or mu by rho is equal to nu. If you know kinematic viscosity, you can use kinematic viscosity. In such case, it is VL by nu. Okay, don't get confused. Rho VL by mu or VL by nu. Both are one and the same. And please don't get confused REX meaning, RE suffix X meaning only to a particular length. At a particular X value, you are calculating Reynolds number. Then your heat transfer coefficient thus calculated will also be at that X value. REL means Reynolds number calculated at the full length of the trailing edge. Or, REX bar is something else, average. That is over the entire region. That's what I said. And for a flat plate flow, the critical Reynolds number value is 5 into 10 power 5. The critical Reynolds number value is 5 into 10 power 5. What do I mean by that? You calculate Reynolds number, maybe the problem can be like this. Problem can be like this. A plate of 2 meters by 3 meters or 2 meters by 3 meters length is kept horizontal. On top of it, some fluid is flowing at a velocity of 3 meters per second or 2 meters per second, and it has a temperature so on. Now, the fluid is flowing on a plate for 3 meters all along it. 2 meters is the width, let me say 3 meters is this. Okay. Okay, so if a fluid a plate is kept like this at 2 meters and 3 meters length, fluid is flowing, let me say its velocity is v and its density is rho. And I said for all flat plates, straight away take it. L is the characteristic dimension. LC, characteristic dimension is L. Where do you use this LC? I said you use it in Reynolds number or rho V L by mu. Okay, rho this. Okay, rho V L by mu. And here you use this L. L should be LC. Nusselt's number also you use HL by K. Prandtl number is mu Cp by K. There is no length term. So what is that L that you use in Reynolds number and Nusselt's number? It is the length along the fluid flow direction. If you want what is Reynolds number here, it is rho V into 3 divided by mu. 3 is what? Length. If you want Reynolds number here, and you should know, I say x equal to 1.5 meters, let me say. Then L should be equal to 1.5 meters. So it is the length along the plate. Please don't get confused. The characteristic dimension is always a flat plate flow, not for everything, only for flat plate flow. The length along the fluid flow will be the characteristic. Now, when I take a two-dimensional view of it, you have a 3-meter plate. When boundary layer is drawn on it, it will be laminar for some distance and turbulent for some. Initially it is laminar, then after it is turbulent. Okay. Now you are curious when the Reynolds number is changing from laminar to turbulent. Or you may have a doubt whether the fluid flow over the entire plate, whether it is laminar or turbulent. So, to decide the nature of the flow, you need to calculate Reynolds. Say, for example, for this plate, I calculated at L, REL. REL, let me say, I got it as, 1 into 10 power 6, let me say. So, once you get a Reynolds number, you always compare it with the critical Reynolds. Critical Reynolds number is what? It is the Reynolds number which distinguishes between laminar and turbulent. Or it is at that Reynolds number, laminar flow starts its tendency to turn into turbulent flow. So, that Reynolds number where fluid flow changes from laminar to turbulent is critical Reynolds number. What is the critical Reynolds number for a flat plate? It is 5 into 10 power 5. 5 into 10 power 5. For a flat plate. And any value less than 5 into 10 power 5, we say laminar. Any value greater than 5 into 10 power 5, we say turbulent. Now, in this case, please listen. Too many things I have written here on the screen. You have calculated Reynolds number here. It was found to be 1 into 10 power 6. What is the critical value? 5 into 10 power 5. Now, is it greater than that? Yes, it is greater than that. So, what is the nature of the fluid flow here? It is turbulent. Agreed. It is turbulent. Now, I'll ask you a further question. Is it turbulent right through the plate right from the beginning? Normally it is this. Please understand, as the fluid flow enters onto the plate region, solid region, initially it tends to be laminar at least for some distance and then turn into turbulent. So, when you find the flow to be turbulent at the trailing edge, this is trailing edge, this is leading edge, I told you. When you find the flow to be turbulent at the trailing edge, the fluid flow is changing from laminar to turbulent. The X value enta. What is this X value? Ekkada flow transition is happening. And a question adiginappudu, you should be in a position to calculate. How do you calculate this X distance? How do you calculate this X distance? Now, let me say this is critical Reynolds number. What is critical Reynolds number? 5 into 10 power 5. What is this? It is equal to rho V X by mu. Rho V X critical, let me say. This is the X critical. And the X critical, when I say XC, when I say, it is at that point flows starting from laminar to turbulent. So, you know rho V mu and you know the standard value of critical Reynolds number, you can calculate XC. So when once you calculate XC, then you will be in a position to say, okay, till that distance it is laminar, thereafter it is turbulent. And normally, in a plate of longer distance, when laminar is for a short distance, particularly with high velocities, we assume that fluid flow is turbulent right from the beginning. Or there are cases where people use turbulent generators right from the beginning. So assumptions can be fluid flow patterns on a flat plate can be it is laminar completely towards the end of the plate. When is that? When you calculate Reynolds number at the trailing edge, when its value is still less than 5 into 10 power 5, entire flow is laminar. చివరిలో నువ్వు రినాల్స్ నెంబర్ క్యాలిక్యులేట్ చేసి దాని వాల్యూ ఇంకా కూడా 5 into 10 power 5 కంటే తక్కువ ఉంటే త్రూఅవుట్ ద ప్లేట్ అది లామినార్ ఫ్లోనే. ఎందుకంటే చివరిలో కూడా అది లామినార్ ఫ్లో వాల్యూని దాటలేదు, క్రిటికల్ వాల్యూని దాటలేదు కాబట్టి ఎంటైర్లీ ఇట్ ఇస్ లామినార్. Or the other possibility is the trailing edge, the value was greater than critical Reynolds number, therefore it is turbulent. And that means for some distance it is laminar and for remaining distance it is turbulent. Or you can assume that because the plate is long, laminar region is very small, you can ignore that. Assume that the entire plate is turbulent. So all these three possibilities are there for you in the calculation, right? So I have calculated what is critical Reynolds number. For a parallel plate, it is 5 into 10 power 5. Okay. So all these equations, I think I have given it to you. All these equations I have given it to you. These equations are available in your data book. You calculate delta T. I think we have discussed about them at length. Therefore, I need not spend time enough here. Okay. So heat transfer coefficients for laminar and turbulent, you have different equations. And again, these heat transfer coefficient equations, again, they are available in your data books. I think all of you who are pursuing heat transfer, you are fully aware of these data books. For different Prandtl numbers, you find different equations. For different ranges of these, limiting values also there. So for all this equation, you cannot apply for Prandtl numbers less than 0.6. You can apply only for Prandtl numbers greater than 0.6. Please remember, there's an expression for NUX. What do you mean by that NUX? You get HX. That means what? You get local heat transfer coefficient. That's not average heat transfer coefficient. For laminar, you multiply that with 2, right? And turbulent, this is the equation. I just request you to please go through any standard textbook to understand local heat transfer, average heat transfer, laminar flow and turbulent flow equations. equations wise. Okay. So these relations are for isothermal and smooth surfaces. What is the condition? Surface should be smooth. Isothermal means the entire plate will be at the same temperature, constant wall temperature, let's say. Okay. And this is it. For combined laminar and turbulent, I said for some region it is laminar, for some region it is turbulent. You have different sets of equations. Different sets of equations. Now, in laminar flows, initially the heat transfer coefficient slowly decreases on spares. We use critical Reynolds number, okay, as greater than close to 5,000. Okay, so some of the visualizations. Okay, I know. I just only to demonstrate how fluid moves behind the ball, behind a sphere, behind a cylinder at different velocities. Nothing much important. Effect of surface roughness. Like I said, surface roughness always plays a very, very important role because I said very explanation of convection heat transfer. I said, no slip conditions. Meaning, when fluid molecules come in contact with the solid plate, they sit pretty on it, no slipping, no movement. And it is more so for a considerable distance in the y direction when it is a rough surface because the frictional effects will be more and more. Just now I said a cricket ball released on one half it is rough, one half it is smooth. And with the minimum skin friction on one side, with maximum skin friction on the other side, ball is going to take a curved path. So all this we can attribute to the roughness on the surface. Okay, so the drag forces, both skin as well as the pressure drag, you can talk about. Okay, I just leave it. Flow over a cylinder, this kind of an equation. Anyhow, I'll share this presentation to you. Maybe I think it's already placed, I believe. Yes, it's already placed. Please go through. For flow over a sphere, you can use this equation. Now, there is nothing in this equation. Please remember, Nusselt is hd by k. But please remember here, for a flat plate, it is the length along the fluid flow, which is a characteristic dimension. For external flows over a cylinder and a sphere, the characteristic dimension is its diameter. Meaning, when such flows are happening, the diameter of the ball becomes its characteristic dimension. Okay. So in all these cases, it is not the length or it is not the length of the cylinder. It is only the diameter that forms into characteristic dimension. So for all these cases, please you need to note flow over a cylinder, flow over a sphere. Over in the sense it's not through it, on top of it. So in all these cases, characteristic dimension is d. So even when you calculate Reynolds number, you use rho v d by mu, not rho v l by mu, rho v d by mu. So Nusselt's number is hd by mu. Prandtl number is mu cp by k. It is not changed. So other than constants, only these three numbers are in picture. Whether the equation is complicated or less complicated, all this. Only in this case you have the viscosities. Okay, right? So what is this indicating? The characteristic dimension for all external flows. Cylinder or sphere, it is d. For a square plate, it is d again. And it is a vertical height. That's what I mean to say. When a solid is placed in a fluid medium, what is the vertical height of the solid? Now in this case, look at it. It is a square plate tilted by 45 degrees. Then its diagonal becomes the characteristic dimension. Hexagon, it is in this case, this is the height. So simply, it is the height of the plate. It is the height of the plate that's used. Okay. So again, the treatment is slightly different when the fluid flow is happening over one cylinder or when fluid flow is happening more than one cylinder. And tube bank, when I say, like your refrigerator, whenever you touch the back of refrigerator, there are, tubes, number of tubes all aligned in the same plane. Okay, and that's one layer tube. So you can have number of layers also. So bank of tubes, it can be a matrix of tubes, and when you have more than one tube forming into a bank of tubes, you need to follow a different set of equations, and all these equations, the pitch and the spacing between the tubes, all these geometrical things are given in your data book. So you can use them and calculate. Again, the characteristic, the parameters of the fluid, you are going to estimate at, film temperature or the average temperature between surface and this. So far, I have talked to you about flow over a flat plate and flow over a cylinder or a sphere and tube, bank of, uh, cylinder tubes, cylindrical tubes. So all these equations, everything is same. It's all about calculating Prandtl number, Reynolds number, and us. That's it. But make sure that you are fully aware of the characteristic dimension. You are fully aware of characteristic dimension. For flat plates, it is the length of the plate along the fluid flow direction. And again, let me clarify. Having said that, this just struck my mind now. If a plate like this, okay, fluid flow is happening in this direction. Say I said in the earlier example, it is 3 meters, and therefore LC will be 3 meters for you. When you are calculating here, anywhere else, what is the X value? If the fluid flow is happening in this direction, then your LC will be equal to 2 meters. So it's always the length of the plate along the fluid flow direction. If it is flowing in this direction, it is 3 meters. If it is flowing in this direction, it is 2 meters. Please don't get confused. Right. So summary, I said drag and heat transfer in external flows, friction and pressure drags, we did discuss about it. Heat transfer, we did discuss about it. And also we talked about, the hydrodynamic thermal boundary layers and the dimensionless numbers, all the three dimensionless numbers, three fundamental dimensionless numbers. What are they? Reynolds, Prandtl, and the Nusselt's number. What are the derived numbers? Peclet and Stanton number. What is Peclet? Product of Reynolds and Prandtl. What is Stanton? Nusselts divided by Peclet or Nusselts divided by Reynolds Prandtl. Okay, so I've shown it there. So over flat plates, across cylinders and spheres, across tube banks, this is what we have discussed. Okay. Now it is exactly 1 hour. So I just give you 5 minutes of break. I'll come back, talk to you about natural convection. So friends, those who missed, because there were many requests, and therefore I had to, at least the very fundamental concepts, I had to repeat it again. There were so many requests. Okay, so thank you. Now I'll come back after 5 minutes, talk to you about natural convection, how we calculate. Yeah. There is a tube flow also, forced convection. I'll first take it up and then come to natural convection. Thank you. Are we there? So welcome back. The force of convection, internal flows. Force of convection, internal flows. That means so far what did we discuss? Only about external flows, meaning fluid flow taking place over a flat plate, fluid flow taking place over a cylinder, fluid flow taking place over a sphere, and bank of. So that means what? All along the tube, around 360 degrees, boundary layers start forming. Okay, how do I explain? I don't know. So a boundary layer starts forming from everywhere. Okay. So from every point, a boundary layer starts going into the tube, right? So as if fluid is going inside. These boundary layers also start at the tip of the tube, where exactly the first fluid is going. There will be zero, and slowly it starts increasing in the boundary layer. So all around 360 degrees it happens. But when I take a two-dimensional view of this, one boundary layer is forming here, another boundary layer is forming here. Okay. Somewhere, if you go to a greater distance, these boundary layers will intersect somewhere. Okay. So you see, the boundary layers are intersecting here. Now, the fluid flow, where the boundary layers are not intersected, the length over which the boundary layers are not intersected, even now they are not merging with each other, intersecting with each other, then such a flow is called developing fluid flow or underdeveloped fluid. And fluid flow, when once the boundary layers intersect with each other, we call it, fully developed flow. Hereafter, you see, hereafter, when once the boundary layers merge, we call it as fully developed flow. Now, you may ask me a question whether necessarily for all fluid flows through conduits and tubes, there will be fully developed flow. Maybe or may not be. If the tube length is only this, there will not be. If the tube diameter is very high, may not be. Because I said the boundary layer thickness is quite small, into order of few millimeters. So if it is a small pipe, small diameter pipe, the chances of getting a fully developed flow is very bright and high. And also, length of the cylinder also plays a very important. Even for a small diameter cylinder, if the length is very short, even at the exit also, maybe the boundary layers may not intersect. And therefore, the developing fluid flow happens all through. Whereas, when length is considerably high, for small diameter tubes, the fully developed flow is quite possible. And at the fully developed flow, the boundary layer, when the velocity profiles will be so. Zero velocity at the tip, as you move at the surface, as you move away from the surface towards the center of the tube, are you watching? The velocity vectors are bigger and bigger. That means the magnitude is higher and higher, means velocity is increasing. And similarly, from the other side, velocity is zero at the surface, slowly the velocity is increasing, and finally, at the center, where the boundary layers are merging, the velocity will be the free stream velocity. Because what happens on the top of the boundary layer? Boundary layer definition itself is this. It is all the joining of all such points where the velocity for the first time is equal to free stream velocity or 0.99 times free stream velocity. So therefore, at the center, at the core of the tube, along the central line of the tube, the velocity will be equal to free stream velocity or the maximum velocity. When the boundary layers are intersecting and moving against each other, even at the center, you may not get free stream velocity. But one thing, please remember, the maximum velocity of the fluid occurs along the center line of it. Please don't forget. That's why L by D ratio, length by diameter ratio, is very, very important in case of fluid flows. Okay. Now, in all these fluid flows, fluid flows, again, we have maybe a tube, or it can be a duct, or it can be any cross section. It can be a triangular duct, or it can be hexagonal duct, any cross section. So when a fluid is flowing internally through these ducts and pipes and channels, then the characteristic dimension LC is equal to 4 AC divided by perimeter. What do I mean by that? See, in a flat plate, you said LC is equal to L along the fluid flow direction. For external flows of cylinder as well as sphere, it's all LC is equal to diameter. And for other configuration, I have shown it there. Now, what is the characteristic dimension here? It is 4 AC by wetted perimeter. Wetted perimeter. What do I mean by wetted perimeter? Perimeter for which the fluid is wetting it. Now, for a simple case of tube flow, it is 4, the area of cross section is what? Pi by 4. Sorry. Pi by 4 d square or pi r square, whatever. Okay, divided by pi d. Pi d is the perimeter. 4 into area of cross section divided by perimeter. So 4 gets cancelled, pi gets cancelled, LC is equal to D. For a square plate of A, you apply the same formula. You need not worry about all this. But you should know for a cylindrical tube, for a circular tube, it's LC is equal to D. For a square plate of side A, LC is equal to A. You apply it here, area is A square, perimeter is 4A, and therefore it becomes A. So for any complicated, configuration also, you can calculate using it. For annular flows, let me say a fluid is flowing through these tubes. I mean, in the annular space between the two concentric tubes. In the gap between them, when they are concentric to each other, how it is. Let me say this diameter is small d. Let me say this diameter is capital D. Again, you can apply the same old equation. It is 4 into area of cross section of the space, annular space. It is pi by 4 into d square minus small d square divided by perimeter pi into d plus d, because the fluid wets this perimeter as well as this perimeter. That's why we call it as wetted perimeter, and therefore when you calculate LC, it is capital D minus small d. Okay. Similarly, you can calculate for square, annulars, any kind of configuration. It's simple. It is cross section area of this divided by 4 into cross section area of that divided by perimeter of this and perimeter of that. Okay. So this way, you calculate the characteristic dimension of any configuration. It can be circular tube, it can be rectangular, it can be triangular, whatever. So one thing I have clarified, characteristic dimension is what. Why you want characteristic dimension? I said the two equations. Nusselt's number is equal to HL by K and Reynolds number is equal to rho VL by mu. L is D here in this case of a circular, right? This one. And to calculate this, what are the three dimensionless group numbers you calculate? Reynolds and Prandtl. From there you calculate Nusselt's number. So the properties like you need rho mu v rho mu K CP. All these values you need. Certain times, for all these gases, data book straight gives you Prandtl number. In such case, you don't need CP. Okay. So the properties, where do you estimate? In this kind of pipe flows, you will have three temperatures. One is a wall temperature given for the pipe and entrance temperature Ti, the exit temperature T0. See, food at a temperature of 100 degrees is entering the pipe. It is giving some heat to, the same fluid is flowing through the pipe. It is giving some heat to the wall and from there it is convecting. And as the fluid is moving through the plate, it is giving away its heat and therefore the outer temperature reduces and therefore T0 is obviously less than Ti in case the fluid is hot. In case the wall is hot, enters at lower temperature, acquires the heat and exits at a higher temperature. So, invariably in internal flows, you come across three temperatures. What is that? The wall temperature, if wall temperature is maintained constant, and the inlet and exit temperatures. So, where do you estimate these properties? Earlier you were estimating at TW plus T infinity divided by 2. But this time you are coming across three temperatures. The film temperature is now, we call it as BM, bulk mean temperature, which is TW plus TI plus T0. Oops. I'll write it here. T bulk mean temperature is equal to TW plus Ti plus T0 divided by 2 whole divided by 2. What is this? Don't get confused. The properties like rho, mu, K, Cp, fluid temperature, to estimate the properties at bulk mean. So, when fluid is flowing through a pipe, the critical Reynolds number for all internal flows will be 2300, unless otherwise specified in the problem. In the problem, you may 2300. I once again write. In the problem, you may say the critical Reynolds number is 2100, and don't ever say you are fixed to this value. No, unless otherwise specified, you take it as 2300. When it is specified, that value you please take. So, critical Reynolds number is 2300. When the Reynolds number is greater than 2300, it is laminar. Less than 2300, it's laminar. Greater than, it is turbulent. So, again here you have turbulent and laminar flows. When a fluid flow is happening through the pipe such that you got Reynolds number as laminar, then you have two Nusselt's number equations. Nusselt's number is equal to 3.66 for constant wall temperature. That means what? The wall is maintained, say problem says the cylindrical wall is maintained always at 90 degrees centigrade. Meaning all along the cylinder, the entire cylinder is maintained at 90 degrees centigrade. How it is maintained, we don't know. When they give such a condition, and if you find the flow to be laminar, Straight away it is not in terms of Reynolds and Prandtl, it is a constant. And Nusselt's number is equal to 4.36 for constant heat flux. What do you mean by constant heat flux? If you have a pipe like this and steady amount of heat transfer is taking place to the pipe, I mean, say a problem statement can be like this. 500 watts per meter square of heat is convected on the outer surface of the plate. Meaning what? Q, small q, is 500 watts per meter square. It's a constant one all along the tube. For every meter square of area, 500 watts is the heat transfer taking place of the pipe. So when such constant heat flux is there, your Nusselt's number is equal to 4.36. When it is turbulent, there's one famous equation called Dittus-Boelter's equation. It is 0.023 Re power 0.8 and Prandtl number power n, where n is equal to 0.4 for heating, n is equal to 0.3 for cooling. Okay. If the fluid is getting heated, meaning what? Plate is at a higher temperature, fluid entry is 30 degrees centigrade, means fluid is heating as it is moving through this. So you use n is equal to 0.4 and n is equal, this is a very popular equation. T is, sorry, it's not T. I'm sorry. It is Nusselt's number. Nusselt's number is equal to 0.023 Re or 0.8 Prandtl number. So entire turbulent flow or laminar flow, forced convection happening, it has certain velocity, right? Certain velocity, so you can calculate. Some of the important things that you need to talk about is the velocities. Because to calculate Reynolds number, you need rho v d, of course, in this case, divided by mu. Okay, mu, of course, is there. V is velocity, right? V is velocity. Now, in a problem, it can be given 3 meters per second, the velocity with which the flowing fluid. What is it? Mass flow rate is given by rho AV, continuity equation. Is you straight away use the mass flow rate. I mean, you calculate velocity from mass flow rate. So with this, probably the turbulent flows through internal flows I've explained. What is that? A developing flow, fully developing flow, velocity profiles in that. What if it is laminar? What if it is turbulent? Critical Reynolds number is 2300 and characteristic dimension is 4 AC divided by weighted perimeter. I did not say anything else. And I also said the fluid properties are taken at bulk mean temperature. What is bulk mean temperature? It is average of plate and average fluid temperature. TW plus TI plus T0 divided by 2 whole divided by 2. Okay, that's all. Now we move on to natural convection. And see, we know that if the air molecule is heated, it vertically goes up. If it is cooled, it comes down, like your domestic refrigerator concept, whatever that I have explained. I think I have given enough number of examples. So these are the examples. If it is a hot egg, egg around the egg acquire the heat and they move up. If it is a cold, cool drink can, just taken out from the refrigerator and kept it on the table, air coming in contact with it become cooler and they become heavier and therefore they come down instead of going up. So whether they go up or come down depending on whether the fluid is getting heated or cooled. When the fluid gets heated, when it is coming against a hot plate. When it is cooled, when it is coming against a cold plate. So that's as simple as that. So the buoyancy forces, fundamentals of physics, you please. Huh? go through it. And we need to talk about the volumetric coefficient of expansion. Here we come across, that is beta. Beta for an ideal gas is 1 by T. Normally, for all beta values, volumetric, because you use volumetric coefficient of expansion in the buoyancy force equation, and therefore it is 1 by T, 1 inverse T, where T is the temperature at which the fluid is, or the average temperature, whatever you consider. But the only thing is, beta is always expressed as Kelvin inverse, 1 by K. That means what? Please remember, whenever you calculate beta in natural convection, you substitute the temperature value. You substitute the temperature value only in Kelvin. Only in Kelvin. Please. What is an ideal gas? PV is equal to MRT. That's an ideal gas. Okay. So whenever you calculate beta, I just cut the whole story short. Beta is 1 by T, and volumetric coefficient of volumetric expansion coefficient, whenever you want to calculate, substitute the value of temperature only in Kelvin. If it is in degree centigrade, add 273.15 and convert that into Kelvin. Okay. So now in forced convection, we talked about Nusselt's number, Prandtl number, Reynolds number, Peclet number, and Stanton number, Nu divided by Peclet. Okay. In natural convection, we do talk about Nusselt's, because Nusselt's is one which gives you H value. So H is there for both forced convection as well as natural convection. And there is Prandtl number whenever there is a fluid, because it is purely based on fluid properties, mu, Cp, and K. Mu is a property of a fluid, Cp is a property of a fluid, K is a property of a fluid. Okay. Now the Reynolds number is replaced with Grashof number. Okay. Now what is Grashof number? It is the ratio of, I'm sorry, I'm not writing because it's not very easy to write here. It is inertia force to viscous force multiplied by buoyancy force divided by viscous force. Inertia force to viscous force multiplied by buoyancy force to viscous force. So it is viscous force square in the denominator, right? Inertia force to viscous force, it is Reynolds number. And you will be surprised, in forced convection there is the inertia of the fluid molecules. Where is the inertia in natural convection? Fluid is not moving, only the molecules keep moving up and down, and there also you come across inertia. Don't get confused. Whenever the molecule at a molecular level, they come across the inertia. Okay. So viscosity is always there. Buoyancy is now coming into picture. In forced convection, you are forcing the fluid to flow in a particular direction, and therefore en masse the fluid moves in that direction because you have created a pressure differential. Now in buoyancy with natural convection, the heated molecules go up, and therefore the buoyancy force. When you compare two molecules adjacent to each other, one is attracted to the gravity. Every molecule is experiencing gravitational force. What is it? Mass multiplied by acceleration due to gravity. What is mass? Density into velocity. What is mass? Density into velocity. What is density? Density, let me say rho dash and rho. Rho is for one particular temperature. Let me say rho dash is for elevated temperature. For when multiplied by volume into G, and for the same fluid at a different temperature, it is rho Vg. So this mg is different from this mg. If it is heated and density is less, this mg is lesser force. Okay, whereas this mg is greater force. When mass is more, the gravitational pull is more. When mass is less, gravitational pull is less. When his mass is less, when density is less, mass is less. So therefore, gravitational pull is less. So both are being pulled simultaneously. Now, this is being pulled at a greater force, whereas this is not being pulled at a greater force. So all neighboring colder molecules are pulled, and therefore this has to pave way for the new incoming colder molecule. This has to float. Slowly, as the colder molecules are pulled towards due to gravitational pull and pulled towards the Earth. Now, slowly, this lighter molecule will have to pave way for these heavier molecules to come and settle. Slowly, this moves. Okay? So, that's how the buoyancy force is experienced. Maybe I tried to explain buoyancy force in as simple terms as I can. So, so this is it. And there is a derived number, even in natural convection, which is called Rayleigh number. Rayleigh number is GR multiplied by PR. Rayleigh number is Grashof number multiplied by Prandtl number. I think Russell's number is HL by K, Prandtl number is mu Cp by K. You know that. And Grashof number is equal to G beta delta T L cubed, because temperature difference is the driving force for buoyancy, right? G beta delta T L cubed divided by nu square, where L is characteristic dimension. Here also you need characteristic dimension 1 in Nusselt's number, which is HL by K, in Grashof number G beta delta T L cubed by nu square. Or if you want it in mu, GR is equal to rho square G beta delta T L cubed divided by mu square. So mu by rho is nu. Nu is kinematic viscosity, mu is absolute viscosity. I don't think I need to explain. Where G is acceleration due to gravity. The 9.81 meters per second square. So that's a universal constant. Beta is 1 over T. Beta is 1 over T. Delta T is the temperature difference between plate and the fluid. L is the characteristic dimension. Now, very quickly, we talk about the characteristic dimensions and the orientations. Now, let me talk about natural convection over a vertical plate. In a vertical plate, what do I mean by that? A plate is kept vertical. Let me say, let me take two cases. One is TW, and this is T infinity. On one side of it, you have fluid, and in this case, I say TW is greater than T infinity. Meaning what? Cold fluid is participating in convection heat transfer with a hot wall. Now, in this case, let me also talk about a wall with a different temperature, fluid with a temperature, and let me say TW is less than T infinity, meaning hot fluid coming in contact with a colder plate. Both are possible. Now, what will happen? In both these cases, when vertical plate is there, in both the cases, LC is equal to height of the plate. LC equal to height of the plate. Characteristic dimension is its height, L. Okay. Whatever is the vertical height, that is it. If a cylinder is placed vertically, it is the length of the cylinder, the characteristic dimension. Please remember, for all natural convection, I am talking about natural convection, for all natural convection, the vertical plate height will be the characteristic dimension. Now, what will happen here? I think I have drawn too many things here. I once again take a fresh board. Now, TW is greater than T infinity. TW is greater than T infinity. That means what? It is hot. Maybe 80 degrees centigrade TW, 30 degrees centigrade T infinity. Now, what will happen The fluid is moving all around this plate, and those molecules which come in contact with the plate, right, which come in contact with the plate, they stick on it. They settle on it because heterogeneous friction. Now, this molecule, which is sitting pretty on the plate, acquires the plate temperature. It was earlier at 30 degrees centigrade. Because it came close to the plate, it is now at 80 degrees. When it is at 80 degrees centigrade, what happens to its density? Temperature and density are inversely related. When temperature increases, density decreases. So this becomes lighter. This lighter fluid molecule would like to vertically move. This lighter fluid molecule would like to vertically move. Now, can it move up? No, it cannot move. Though it has lost its density, because it is sitting pretty on the intricate gaps in the surface. Even for a smooth surface at a microscopic level, you have irregularities. And also the heterogeneous friction, wall and molecular friction. Molecule will have certain viscosity, and therefore, it's sticking very pretty, sitting very. Though it has acquired the temperature of the wall, though it lost its density, it cannot move up because friction is prevented. Whereas the next layer of molecule, which come here, now it is interacting, it is not interacting with the plate, it is interacting with another fluid molecule which is sitting pretty there. No, which is not moving there. Now this molecule also acquires, maybe it may not be 80 because it's not in physical contact with the plate, and residence time is not also as much. Maybe this time it is 75 degrees centigrade, this much. But it is again in the close proximity to the plate and also coming in contact with the previous molecule which is at 80 degrees centigrade. So it loses its density and it wanted to move up. Buoyancy force causes it to move up. Now, when it is moving up, it is rubbing against the same old theory. It is rubbing against the stationary molecule, and therefore, though the buoyancy forces match, experienced match, because it is in a 75 degrees centigrade in a 30 degrees centigrade medium. So it wanted to vertically move up, but then the inertia of the molecules at rest pulls it back steadily. Slowly, as they move away from the plate, the velocity increases. Somewhere it reaches a maximum, and thereafter velocity decreases. Why? Can someone explain me why the velocity decreases here? Because as you are moving away from the plate, the temperatures will not be very high. So somewhere it started here, temperatures are high. It wanted to move, but then friction and inertia both are coming in picture here, and therefore slowly as you move away, the frictional forces are reducing, and therefore molecules start moving. And somewhere the minimum friction is experienced as you have comfortably came out, and therefore velocity is maximum. If you go further, this molecule temperature will not be very high because it is far away from the plate, and therefore, though the frictional effects or viscous effects are not felt here, the frictional and the initial effects are not felt here, but the buoyancy force is less. The very driving force is less because it's away from the plate. And the 70 degrees centigrade load, it is 50 degrees centigrade. So 50 degrees centigrade fluid molecule against 30 degrees centigrade, though buoyancy is there, but the force is not much, and therefore it moves slowly. So if you finally ask me to draw a velocity profile, the boundary layer still exists here, and within the boundary layer, the velocity profile is like this. And it is all organized. It is vertically moving up because the plate is at a higher temperature. The plate is at higher temperature, and therefore it heats the fluid. Fluid loses its density, moves up. So a velocity profile of this can be seen, okay, slowly as it decreases. And after this boundary layer, no particle is moving. Why? Because it is a natural convection. Natural convection, you don't have an organizer motion of the fluid particle, and therefore fluid particles are stationary, quiescent, and in the sense bulk motion of the fluid is not there, and therefore a stationary medium of the fluid Only this temperature and related buoyancy forces cause this vertical motion. This is the velocity profile. Similarly, you can also talk about temperature profiles. What is this temperature profile? The molecule which is sitting on the plate, okay, this will have a temperature of TW. This will have a temperature of TW. And the next molecule will not be at the TW, and slowly, as it moves away from the plate, it decreases. Finally, it reaches a 30 degrees centigrade. Thereafter, it is a horizontal 30 degrees everywhere because the plate, they are far away from the plate. The temperature effects or thermal diffusivity or heat interactions are not felt beyond this distance. So the temperature profile are this, and when you join all such points where for the first time temperature becomes 30 degrees centigrade, this is a thermal boundary layer. This is a hydrodynamic boundary. So even though in natural convection, fluid is not moving, fluid is not literally moving, right at the vicinity of the plate, because of the temperature variations and buoyancy forces, the fluid still moves within in the immediate vicinity of the plate in an organized way in a particular direction. Okay, so therefore, you can plot a temperature profile as well as a velocity profile. Right. Now, very quickly, without changing, wasting time, if TW is less than T infinity, meaning hot fluid coming in contact with the cold plate, it is giving away heat. Maybe it is 80 degrees centigrade, plate is at 30 degrees centigrade. So the particle which is coming here sits on the plate, and therefore it loses its heat from 80 to 30. It becomes heavier because it lost heat density increases. It becomes heavier, but it cannot move down because of friction. But next molecule is capable of moving down. Now it is downward. Same explanation with the downward. And later on, the temperature drop is not much, so a velocity profile can be drawn like this, and you will have a boundary layer from top to bottom. Okay, fluid starts moving down. Similarly, temperature profile can be drawn. Okay, so an interferometer produces a map of interference fringes which can be interpreted as lines of constant temperature. So an interferometer or any such devices can be used to visualize the fluid flow or the temperature profiles. So that's there are very advanced instrumentation. I just don't want to discuss it right now. Isotherms means constant temperature lines. This is what I have explained it to you, the temperature profile and the velocity profile. And what is this? After hearing me, can you tell me what is this? It is a hot plate and cold fluid because it's moving up. Cold fluid is coming in with contact with the hot plate, and therefore they are vertically moving up. Okay. And there are three equations which are very popular, and you must know about them. One is conservation equations. One is mass balance equations. Second one is momentum balance equations. That's what we call it as Navier-Stokes equation, which talks about the viscous effects. And the third one is energy equation, which talks about energy balance. So mass balance, momentum balance, and energy balance, these three equations are very, very popular. And of that, momentum equation gives plethora of solutions when it is solved for different cases. So that's where, when you are studying advanced fluid mechanics, it is such beautiful subject, with a little bit of knowledge in mathematics, when differentiation, partial differential equations. You can really enjoy solving all such problems on that. So for the time, don't worry. I'll towards the end of it, I'll list out all this energy, momentum, and mass conservation equations. You can go. Okay. So, so it's here. Continuity, mass conservation. Okay, and momentum equation and energy equation. In only x y directions, only two-dimensional variation. This is where this the other name to it is the Navier-Stokes equation. This is where you come across viscosity and all, viscous effects and all. The Grashof number, I think I have already told you, G beta delta T LC cube divided by nu square, where LC for all vertical plates or vertical solids, the height is the LC, and beta is 1 by T for ideal gases, whereas T is always in Kelvin. That's why they always keep it capital T and 1 by K. Don't get confused. Yeah. Okay. What is Grashof number? Grashof number is the product of two ratios: inertia force to viscous force and buoyancy force to viscous force. So, this is something what I have already explained it to you. So, the possibilities of how it moves, for different cases. So, natural convection, now we have seen it for vertical surfaces. Let me see for a horizontal surface. Let me see for a horizontal surface. Now, instead of saying it, I think if you can look at me. See, let me say I have a flat plate, horizontal plate. Now this is horizontal plate. For all such horizontal plates, characteristic dimension is area by perimeter. Whatever is the surface area divided with the perimeter of this. Okay. L into B divided by 2 into L plus B. That's what it is. So, characteristic dimension for vertical plates, it's right. For horizontal plate, it is area by perimeter. Now, when this is a horizontal plate, I have two scenarios. One, the plate is hot. Place it at a higher temperature as compared to the fluid. Now, the fluid molecules come in contact with it, with the plate, acquire the heat. Now, they are not rubbing against them. Straight away, it can vertically move because buoyancy is, there is no rubbing thing. Straight away, it gets detached, it moves up. Buoyancy force is upward because the plate is hot. When plate is hot, a colder molecule at 30 degrees centigrade slowly drifted, came in contact with the 80 degrees centigrade plate, and it acquired the temperature of the plate because it is in physical contact with it. Okay, so now this is 80, its density is decreased, slowly it started buoyancy forces. When it is moving up, it is creating a space there, vacancy there, and immediately next heavier molecule can come in. And it can acquire heat. It is such a favorable condition for convection heat transfer. Convection is so better explained that the molecules coming in contact with it acquire the heat and they vertically move. That's such a beautiful way. Very simple. Absolutely, convection heat transfer is better explained here, and you can very easily understand what happens. Now, we go for a different scenario. What is it? A cold plate. There's a cold plate. There's a cold plate. Hot fluid, 80 degrees centigrade. 80 degrees centigrade fluid is coming in contact with 30 degrees centigrade plate, sticking on its surface. Now it lost its heat, temperature, and it is now at the plate temperature. Now, everywhere here you have 80 degrees centigrade, lower density molecule. All of a sudden, it went to the plate, lost its temperature, gave away its heat, and it is now at a reduced temperature. So, it becomes heavier, density increased. The heavier molecule cannot go up, it sits pretty on it. Now, next molecule comes, it either interacts with the plate or the already settled heavier molecule, water molecule, and it also loses its heat. This also sits heavy. Now, what is happening after some time? Layer after the layer, the hot molecules are coming, giving away the heat to the plate, and now they are settling because they cannot move. They have become heavier. Buoyancy force is reversed now. All these molecules, upon losing its heat, they are coming and sitting here. Now, the plate will be inaccessible to remaining fluid molecules all around. So this hot molecule, it cannot come in contact with the plate. It can only come in contact with the second layer, third layer, or fourth layer of molecule, and they are all sitting in. So when the a ramming kind of an effect happens, they because the density is high, they become heavier. They all try to sit on the plate. Now what is happening? Convection heat transfer is not happening. Heat transfer shall predominantly happen because of convection heat transfer, because all the heavier molecules are settling down, and one to one the molecules layer to layer through vibrations and kinetic energies, whatever they possess due to the collisions, whatever the heat is interacted upon. But the so-called natural convection, if the plate were to be hot, now what happened? The colder molecule came, acquired the heat, increased the temperature, density is reduced, quickly it was going away. But it cannot go away. It all settles here. It all settles. So, for a horizontal plate, there is a favorable condition. The second case I have explained is highly unfavorable. Second case I have explained is highly unfavorable. What do I mean by highly unfavorable? Convection is not happening. The colder molecule is not capable of moving up. So convection is not happening. The same can be explained on the bottom surface. Bottom surface. What is it? When bottom surface is hot, all the molecules coming here, they stick onto the bottom. I mean, they come in contact with the bottom surface. It is already hot, and therefore they lose. They acquire the temperature, lose their density. They would like to go up, but a plate is restricted. The plate is the boundary, and therefore they cannot go further. So all the heated molecules acquire the plate. So colder molecule will not get an opportunity come in contact. That is unfavorable. Meaning what? A horizontal plate, top surface hot is very good. Okay, but bottom surface hot is not good. And at the same time, colder surface, I mean horizontal plate, colder top surface is not good for convection heat transfer. Unfavorable condition. And whereas if it is cold at the bottom, what happens? Hot fluid comes in contact with it, it loses its temperature, becomes heavy, straight away it comes down, like your deep freezer at the top. Straight away, the hot fluid come in contact with it, loses its temperature and becomes heavy, they very quickly come down. So, at the bottom, when it is cold, it is favorable. At the top, when it is hot, it is favorable. For a horizontal plate, area by perimeter, okay? Area by perimeter is the characteristic dimension. Okay. So, this is how I could explain natural convection. Now, the L, for a vertical plates, I said L is the height is the characteristic dimension. The equations are given here. Any data book, any standard data book gives you Reynolds number in terms of Rayleigh number. But again, I should tell you, Rayleigh number is the determining number to decide whether flow is laminar or turbulent. Here also the fluid can be, movement can be tubular when temperature difference is very high. So for all Rayleigh numbers greater than 10 power 9, we assume that the flow is turbulent. For all Rayleigh numbers less than 10 power 9, we assume that flow is laminar. Understood? So what is Rayleigh number? Rayleigh number is a product of Grashof and Prandtl number. Rayleigh number is a product of Grashof and Prandtl number. Okay. So whenever it's an inclined surface, again we use L, the total length of the plate, as the characteristic dimension. But a small correction we use in calculating Grashof number, instead of G, you use G cos theta, where theta is angle with the vertical. Theta is the angle with the vertical, not with the horizontal. You don't measure the angle this, angle with the vertical. If my hand is the inclined plate, angle with the vertical. So small correction that you use is G cos theta when you calculate the Grashof number. Remaining things same. So I told you, upper surface of a hot plate, lower surface of a cold plate, they are favorable. Lower surface of a hot plate or upper surface of a cold plate, no, they are unfavorable. So therefore, you see, the heat transfer, same equations here. Nusselt's number is almost 50% of the LDL. So that's because, see, it is 0.54 into Rayleigh power 1 by 4, whereas it is 0.27 into Rayleigh power 1 by 4. Okay, so the second condition is unfavorable, both on top side as well as bottom side. The first side is highly favorable. Okay, and they don't get confused. The other equation is Nusselt's is equal to 0.15 Rayleigh power 1 by 3, not 1 by 4. So this constant is different because the power is different. Okay. And if I have listed here, what is the characteristic dimension? Area by perimeter. Good. So for a vertical cylinder, it is again L. For a horizontal cylinder, characteristic dimension is D. For a sphere, it is D. And I've told you, the 10 power 9 is the critical Rayleigh number that we talk about. Anything less than that, we call it lamina. Anything greater than that, we call it turbulent. Okay. Turbulent flows, inclined plates, the boundary layers, all this can be discussed. So this is a complicated setups where fins are there, intricate shapes are there. Okay. So this is some reading, maybe you can have a glance through these presentations. Combined natural convection and radiation, when we take up radiation, we'll discuss. Okay. So, my dear friends, actually I thought of solving few problems, but I had to repeat on the request of many people. So I'm slightly behind. Half an hour I have wasted, I thought, today. So I have completed convection. Maybe next class tomorrow. Tomorrow is 19, right? I have another 4 days time from today. Okay, so we should be. One day I talk about heat exchanges. One day I talk about condensation and boiling, and 2 days we'll talk about the radiation heat transfer. So we should be reasonably close to completing the targets. Thank you for your patient listening. Bye bye. Good night.